For most of aviation history, aluminum alloys have formed the skeleton of civil aircraft. From early propeller planes to modern jetliners, aluminum made up the skins, frames, and internal supports that carry flight loads. Its balance of lightweight, strength, and manufacturability made it the default choice long before composites became common. Even today, aluminum remains deeply embedded in aircraft design, especially in fuselages, wings, and secondary structures. Aluminum rose to dominance because it solved many problems at once. It is far lighter than steel, strong enough for pressurized flight, easy to shape into complex forms, and relatively inexpensive. Engineers also understood its behavior well, backed by decades of testing and service experience. Just as important, aluminum structures could be inspected, repaired, and riveted easily, making them practical for large commercial fleets. Structurally, aluminum alloys offer a low density that keeps aircraft weight down, while still providing sufficient strength for flight loads. They have a well-understood elastic and plastic response, allowing designers to predict deformation and failure. Aluminum also shows visible fatigue cracking rather than sudden failure, which supports safe inspection and maintenance. These predictable properties made aluminum ideal for certified aircraft structures. In civil aircraft, aluminum alloys appear almost everywhere. The fuselage skin resists pressurization loads, frames maintain cross-sectional shape, stringers carry longitudinal loads, and ribs define wing geometry. Aluminum is also common in floor beams, control surfaces, and access panels. These parts rely on aluminum's ability to be riveted, machined, and repaired efficiently across the aircraft's service life. One major advantage of aluminum is repairability. Damaged sections can be cut out, patched, or reinforced quickly. Cracks tend to grow gradually, giving maintenance crews time to detect problems before failure. Aluminum also conducts heat and electricity well, helping with lightning protection. Combined with decades of operational data, these advantages make aluminum structures dependable and predictable in airline service. Despite its strengths, aluminum has clear limits. Repeated pressurization cycles cause fatigue cracks to initiate at rivet holes and joints. Exposure to moisture, salt, and pollutants leads to corrosion, especially in lap joints and hidden areas. As aircraft age, small defects accumulate, increasing inspection demands and maintenance costs. These limitations eventually drove the industry to explore alternative materials. As aluminum aircraft age, maintenance becomes increasingly critical. Engineers monitor crack growth, corrosion hotspots, and structural degradation using scheduled inspections and non-destructive testing. Programs like aging aircraft assessments were introduced after high-profile failures to prevent hidden damage from reaching critical size. Managing aging aluminum structures is less about replacement and more about smart inspection, timely repair, and life extension strategies.